In this video, we're going to continue working with the idea of the derivative and focus on it graphically. So looking at this example of a function, we have a piecewise function of three linear functions. And we know from earlier that our function is not going to be differentiable at 2 points here on the graph. At the point of x equal to -2 and at the point x equal to 0, because those are corners. And so we are not differentiable at those corners. However, we can look at the derivative of the rest of the function, which really, remember, the derivative is just a slope function. So what is the slope of our function pictured here? And then we want to graph the derivative. So our goal here is to graph f prime of x, or the derivative, or we're looking at dy dx. And so if we look at this first portion from -5 to -2, we see that we have a slope of -1. So let's make note of that. This slope here is equal to -1. And it's the same for all of that, for all x that are in between -2 and -5, or potentially off into infinity. We don't know. We only have this graph pictured from -5 to 5. Okay, so let's look at the next portion here. Looking from -2 up to 0, we see that we have a slope of +1. And so we transition from -1 to +1 at that x value of -2, and that's why we have a corner, and that's why we are not differentiable at that point, because our derivative is not continuous. All right, and then if we look at our last piece from 0 out to 5, we see that we have a slope of a -1/2. And if we graph all three of those slopes, our derivative function will look like this. We'll have a horizontal line segment from -5 to -2, but we're not including -2, because remember, at -2, our derivative is undefined because we're non-differentiable, and so we're undefined at our derivative, both at -2 and 0. And so this derivative graph gives us a picture of what the slope of our original function is. Let's look at another example here that is non-linear. Now, since it's not linear, we want to look at some key positions. Well, some key points on this graph are going to be when our slope is 0. And so that's going to happen up here, and up here, and then down at this lowest point here. And that is where our tangential slope is going to be 0, or the slope of our tangent line is a horizontal line. If we transfer those points over to another graph, that tells us when our slope function, or our derivative function, crosses the x-axis. So we know at x equals -3, our slope is 0, so therefore our derivative of -3 is 0. At -1, we have the same thing, and at +1, we have the same thing. And so that's where our derivative function is going to cross the x-axis. Now, to find the rest of the function, we have to look at what's happening to the left of -3. What type of slope do we have? Well, we have positive slope. This is moving up in the positive direction. But what's happening to that slope? Well, right here we have a positive value, and it stays positive, but the tangent slope is decreasing and approaching 0. So that is why we want to look over here at the graph of the derivative. We are at positive values, but we decrease until we get to 0 at -3. And then if we look at the next portion, we have a 0 slope at -3, but then we have a negative slope as we go towards -1. But what's happening to that negative slope? Well, that negative slope starts at 0, and it starts to get steeper. It starts to get more negative, but then at some point, it levels out and then starts to get less negative as it approaches 0 again. So at this point, we call that a point of inflection. We'll talk about that more later. But at that point, that is a special point on our derivative graph. That is when our derivative reaches a minimum. And then it comes back up to 0 at -1. So we have a 0 slope there, corresponds with our 0 slope here. So we go down and back up. And then what happens in that next portion from -1 to +1? Well, we have a positive slope. We're moving up and to the right. But what's happening to that slope? Once again, it starts at 0, and then it's starting to get a little above 0, a little above that, a little above that, a little above that, until it reaches this point here, and it starts to decrease again, and it starts to get a little less, a little less, a little less, a little less, until we hit 0 again down at 1. So our derivative function, the slope is increasing, all positive, then it starts to decrease while still staying positive until it hits 0 at x equals 1. And then the final piece, we see that our slope is negative throughout, but what's happening to it? Well, it starts at 0 and then starts to get more and more negative, and it gets steeper and steeper, and therefore we go off to -infinity. Now, we could draw the arrow here and here, depending on what this graph is. We don't know, so we can leave those arrows off. Either way, it doesn't matter. Now, let's look at a graph that has asymptotes in it, and let's try to graph the derivative. Well, this has two vertical asymptotes at -1 and 1, and our derivative is going to have those same asymptotes. However, we're going to try to graph the slope of the function. So looking at what's happening to this slope here when we're to the left of -1, what's happening to the slope here, and what's happening to the slope here. So if we look at the slope from -infinity up to -1, we have a slope that's really close to 0 because we're kind of leveling off and we're getting to some horizontal value and we're getting close to 0. And so this slope is approaching 0 to the left, but as it's coming in, its slope is negative throughout, but it's getting more and more negative until as it approaches -1, it goes off to -infinity. And so the derivative looks very similar to the function itself. However, it's a little steeper sooner, if that makes sense. We're approaching infinity more quickly, and we're not approaching this -1 line where we're going off to infinity more quickly than the function itself is. And so if we look past -1, look to the right of -1, what is our slope of our tangent line here in this function? If we look at the green portion, it's negative, and it's all negative, but what's happening to the negative? We have negatively huge to start with, almost vertical, and then as we come down here, we level off until we're 0, and that 0 happens at some point on the x-axis between 0 and -1. For right now, we're not too concerned about where that point is exactly, but it lines up with that leveling off of the slope. And so it's negative everything between -1 and this point on the x-axis where we're saying the slope is 0. And so after we go to the right of that point, what's happening to our function? Well, the slope is 0, but then it's getting positive, and it's steadily increasing. And so as it's increasing, we're staying in the positive direction, but it's getting bigger. And it goes off to seemingly an infinite slope. We don't see it as it continues up above in the y direction toward this asymptote at x equals 1. And so once again to the right, we're going to look at, well, what's happening here with this slope? Well, this slope is negative, and it's negative throughout, but that it's negatively huge to start with, so that's why we're down here, but then we level off and approach a slope of 0. So the derivative of this function right here, y equals some f of x, is graphed down below, and that is our f prime. A couple things to keep in mind here with differentiability and continuity. If a function is differentiable at a, then we can say that it's continuous at a. All right, so differentiability implies continuity. On the other hand, we can look at a function that is not continuous at some point a, and we see that there's a break here in continuity, and so we can then claim that f is not differentiable at a. And so an alternative version of the theorem we just stated is that if f is not continuous at a, then f is not differentiable at a. So we imply that if a function is differentiable, then it's continuous, or if a function is not continuous, then it's not differentiable. But keep in mind, we cannot say the reverse of this. If we say that a function is not differentiable, that does not imply that it's not continuous. So make sure you read these two versions of the theorem correctly. Differentiability implies continuity, not continuity implies not differentiability.